Hi everybody. Today my topics is to find structural displacement vector using direct stiffness method. In the matrix stiffness method of analysis, the joint displacement of the structure are determined by solving a system of simultaneous equations, which is expressed in the form like this one. Here P, it is a vector representing equivalent nodal loads applied to the structure relative to the global axis. And in short, we can tell it as structural load vector. And this K, it is the structural stiffness matrix relating to the degrees of freedom. It is very important points. And it is at the nodes relative to the global axis. This del, it is a vector representing the displacement, both translational and rotational, of the structure at its nodes relative to global axis. And we call it as structural displacement vector. The structural displacement vector, this one, it can be determined from the product of these two. One is inverse of structural stiffness matrix, another is structural load vectors. Let's move ahead to see details of it. Here it is a rigid jointed frame structure which rests on, here we can see it is a fixed support, a hinge support and a roller supports. And this structure, it carries a number of loads. 50 kilonewton, this is concentrated load. 10 kilonewton per meter, this is uniformly distributed load. Now, in order to generate a structural stiffness matrix and to complete the subsequent analysis, what you will see in the next slides, it is necessary to establish a global coordinate system which defines the position of the nodes and their displacement. We can see here there are three nodes in the structure. The stiffness matrix for an entire structure, it is dependent on the number of structure degrees of freedom, which corresponds with this nodal or joint displacement. These three. Here, this node 4, it is fixed with respect to translation and rotations. So, there are no degrees of freedom here. But for one, I mean at A, it is free to rotate, but it is not free to move in the horizontal directions. Again, this node 2 and node 3, these two are free to rotate. Already I showed here arrow marks to show that it is free to rotate or free to move. So it is free to rotate. So 1, 2, 3. So how many we got? These 3 places it is free to rotate. So there are 3 degrees of freedom. Even we can find it in other way using equations like this. Decay, kinematic indeterminacy, degree of kinematic indeterminacy, how it is 3j minus in bracket r plus m. So j joint, how many joints we have? A, B, C, D. So 4. And reactions, here 3, here 2, here 1. So 6 reactions. How many members we have? 1, 2, 3. So degrees of freedom is 3. One important things I want to mention here, that the size of the structural stiffness matrix will be same as the number of degrees of freedom. So here we can see 3 degrees of freedom. So our matrix will be 3 by 3 matrix. Now here the coefficient for the structural stiffness matrix. What is that? Here I put coefficient for this node K11, for this node K21, for this node K31. How it is named? Because for unit rotation theta A equal to 1, we get force here in terms of moment at this joint, and it will be 4EI over L. And the member connected to these joints are affected with this rotation. Because rotation is 1, our force in terms of moment, it will be 4EI over L. See, if we look at this, so for K11, I mentioned here, it is 4EI over L, so value is 0.67 EI. Now question is, how we get this? If we look at this, member AB, we give rotation here theta A equal to 1, and due to that moment needed 4EI over L, but condition is when we do this rotation, far end must be fixed, and moment generated here 2EI over L, and these two moment are clockwise. So anti-clockwise there will be couple of force, that is 6EI L square, 6EI L square. This is opposite direction of this moment. But details of it, I mean how we get this 4EI over L, in this regard you can visit my another video, then you will get this explanations how to get this 4EI over L. But here we are picking the value only, that 4EI over L. So this K11 it will be 4EI over L, because these joints. We are applying rotation here. But far end will be 2 EI over L. So it means K21 will be 2 EI over L. Let's see that. So it is 2 EI over L according to this. Also I mentioned member connected at these joints are affected with this rotation. Even far end also have impact, what we have seen here. But in this place it has no connection with this joint because only the member connected to these joints are affected, not others. Like this one is not affected. So here K31 surely it will be 0. So we got 3 structural stiffness matrix coefficient K11, K21, K31, and these 3 are the first column of 3 by 3 matrix. Another important things I want to mention here, that as we applied rotation at node 1, so again we wrote 1, it means what is the impact on 1. That is why it is K11. Here 1 due to this rotation at 1, what is the impact at 2? That's what it is here. Again for this one 3 1, so unit rotations for 1 at 1, what is the impact on 3? That's why it is K31. So this way it is written. This one same as the previous one, only the difference is before theta a equal to 1, now theta b equal to 1. Already I told members connected at these joints. So we put rotation here because theta b equal to 1 means we applied unit rotation here. So these joints are, these 3 members are connected at these joints. So these 3 members are affected. So what will be the result then? Here need moment 4EI over L. For this one also need 4EI over L. Here also need 4EI over L. So 3 multiplied by 4EI over L. I mean 4EI over L to be multiplied by 3 or to be added 3 times. So here we can see same way if we applied unit rotations. I showed here 4EI over L. So what is coming for K22? It will be 4EI over L for AB, 4EI over L for BD, 4EI over L for BC, for these 3. So I put here AB, BC and BD. Total we got 3.5 EI. For the second one, we are sure now that it will be 2 EI over L because far end with the same beam. So it will be 2 EI over L. Now it's clear. For this one also will be far end, so it will be 2 EI over L. Two EI over L. So that is the results we have. It will be 0.75. Here actually I wrote here I. It will be EI. I forgot to mention it. Maybe when I typed it was mistaken. But consider 0.75 EI. So this K12, K22 and K32, it will be the second column of stiffness matrix. Same thing, only instead this I put unit rotation at C. Due to that, you see the deflected shape. So 4EI over L needed here. So it will be 4EI over L, and we get the result as this. Again I showed here because I am bringing this again and again to just make comparison with this one. Due to this rotation, keeping far end fixed, we get 4EI over L. So this is 4EI over L. So what is this one? K23, very clear to us. It will be 2EI over L. That's all. And this one, there is no connection with this joint, so it will be 0. So we got here K13, K23, K33, and this 3 coefficient will be the third column of 3 by 3 stiffness matrix. So structural stiffness matrix, we have to get those 3 slides, all the coefficients, total 9 coefficients we have to get here. 3, 3, 6, 3, 9, 3 by 3 matrix. So this is the value we got. I put EI outside. Now we have to find this cofactor matrix. You guys go to matrix analysis, then you will understand how to get cofactor matrix. I am not going to explain this. This is the basics of matrix analysis. So once we get this, let's move ahead to see. Also, we have to find determinant of matrix. It is needed to find invert of matrix. This is the formula, transpose of this matrix, what you got in previous slides, and this is determinant of matrix. Dividing these two, we get invert of matrix. So our result will be like this one. Now we will use this to find theta. But before that, we need to find equivalent nodal loads. How to get that? To find fixed in forces for member AB, the condition is these two joints must be restrained against displacement. That is why we put here fixed support. Here also fixed, here also fixed. So we can find the fixed in forces. As well, I put here mark 1, 3. These two are the forces, and these 2 and 4, these two are the moments. Already I put here the formula how to calculate that. So there will be 4 equations here. It is easy to calculate. Only need to put the value of this 50 and 10 on these formulas. So once we get this, our target is to convert these forces into equivalent nodal loads. Equivalent nodal loads, it means what we have got in the previous slide as fixed in forces we have to use those set of forces equal in magnitude but opposite in direction. Same forces, it will be same value equal in magnitude, but we have to put here in opposite directions. If you compare with the previous slide, you will see this one showing clockwise, but in previous slide it was anti-clockwise. This one showing anti-clockwise, but in previous slide it was clockwise. So equivalent nodal load for AB. This way we have to find for BC. Same style, keeping both end fixed, we have to find the fixed in forces for BC. Now we will use these four forces. It means we will convert these four forces into equivalent nodal loads. Let's see in the next slide. All the forces are equal in magnitude but opposite in direction to the fixed end forces. So equivalent nodal loads for BC. This is vertical members. Hard to read because that is vertical. So I am making it slight inclined to read it easily. Now same way fixed in forces are calculated. So I got all the forces. Now equivalent nodal loads for BD. Same way we have to apply it. Set of forces equal in magnitude but opposite in directions. So we are getting P1, P2, these three here node, there are three members, so we have to add all these values. So for this node we got this 69.17 minus. For this one we got minus 13.33 kilonewton meter. Here kilonewton meter. This is all our moments. But one thing we have to look at, these two are here. It is clockwise. But it is showing here negative and negative. So we have to change the directions. You see, direction is changed. So we got these three structural load vectors. So this is the vectors we got, structural load vectors. We will use this vector to find theta. rotations. Structural displacement vector we will calculate using this. So we will use structural displacement vector we will find using this, and then K inverse, invert of matrix stiffness matrix. We already calculated it in previous slides. This is the load vectors, and multiplying these two we get theta A, theta B, theta C. So we got theta A, theta B, theta C in radians. Here I mentioned it is radians. This is the deflected shape of the structure. And here the rotation. Using these three rotation, we can write structural displacement vector. So we got it, structural displacement vector. That's all for today. Thanks for watching.